Hi everyone, this is another modeling example. So we're trying to write a formula for a function that models some real world situation. This one is a little bit messy. There's a lot of pieces you have to bring together, but I really like a lot of those pieces. So I continue to use this one because I think it's pretty good practice. Okay, so we have someone walking in the desert, and the situation can change. This situation is a little silly, but the picture and the general idea of the setup stay the same, even if you change the story with it a little bit. So she likes to walk in the desert. She's able to walk 2 miles per hour when she is in the desert, and 4 miles per hour when she's on roads. She is trying to get to the parking lot as quickly as possible. She's out in the desert right now, 1 mile from the road, and the parking lot is 2 miles down the road from a point straight across from her. So I didn't print the picture here, but I will give it to you right now. So she is 1 mile straight out from the road. So let's say this is the road down here. And from this point right here straight across from her, the parking lot is 2 miles down the road. So right here is the parking lot. We'll just give that a P. So her goal is to get back to point P. Rather than just cutting straight across to point P, she's going to walk at an angle so that she runs into the road a little before point P. And then she'll continue down the road until she gets to the parking lot. We have a variable defined. She's walking at an angle so that she reaches the road X miles from the parking lot, which means this length right here should be an X. We are trying to write a function that gives the total time that it takes for her to get back to the parking lot, depending on the value of X that's chosen. So again, the calc version of this problem would be the exact same setup, but we would be looking for the value of X that gets her there in the least amount of time. So this would be a minimized time problem. So what we're balancing out in this situation is if we cut straight across from where Sue is standing now to the road, there are some advantages. In particular, that's the shortest possible distance. If any route we could possibly pick, that one is the shortest route in terms of distance. The disadvantage to that option is that she walks a lot slower in the desert. She's twice as fast when she hits the road. So even though the distance is shorter, she's going at a slower rate, and that might not work out well if her goal is to get there quickly. The other extreme that I see here is she could head straight to the road and then follow the road all the way back to the parking lot. The advantage to that one is she gets to the road in the least amount of, yes, I think time is fair to say. She gets to the road more quickly. And then when she's on the road, she walks a lot faster. So that is a good thing, but balancing that out is the fact that this is the longest possible distance route that I think we should even consider. It is possible for her to backtrack and then head down the road, but I can't see any reason to consider that one. If you're ever working on one of these and you think you've come up with something a little bit tricky on the domain and you're not sure if I'll get it, just write it out in words for me. So if you're working on something like this on the test and you want to explain why you chose not to let her backtrack, go for it. If you come into tests when I'm proctoring, then you can also ask me something like that. Okay, so back to the time thing. We want her total time to get back to the parking lot. So I think the first important piece to recognize here is first. Yep, I think that is the first one I would point out. That the time has to be broken up into two parts. There's going to be the time that it takes her to walk across the desert and the time that it takes her to walk along the road. So I don't know if that's actually the very first thing you'll notice. Maybe the first thing you'll notice, and it's the other really important piece right off the bat, is I don't actually have any information about time here. All of the information I have is about distance and rate. So I have the 1 mile distance, the 2 mile distance, and the distance x. I have the rate 2 miles per hour in the desert, 4 miles per hour on the road. If I would like to get an equation that tells me about time, I'm going to have to figure out how to get that from distance and rate. So hopefully we all know, if not commit it to memory, that distance is equal to rate times time. If we're looking for time, we're going to say time is then equal to distance divided by rate. So we can set up time information based on what we have. We'll just take the distance and divide it by the rate. So if you haven't already, this is when you should notice that you do have to split this into two pieces, time in the desert and time on the road. The reason we're forced to split the time up into two pieces is because we have everything different about those two. One is that the rates are different for the two different pieces. The other is that the distances are probably going to be different for those two pieces. So again, as much or as little of this writing out in words as you want to do is fine with me. This is just my advice. If you're getting stuck on these, try and break it up into pieces for yourself. And a lot of people get more confused if they make those pieces all have a bunch of different variables in them. So I just write it out in words. Okay, so if I want the time in the desert, what I'm actually going to have to do is find the distance in the desert. Oh, we're making it desert now. Desert, there we go. Divided by the rate in the desert. And then we're going to add the distance on the road divided by the rate on the road. So to calculate a time, I use a distance divided by a rate. However you want to write this out is fine with me. If you have funny abbreviations in there, I don't care. This part is just your work to help you get going, so don't get too caught up in trying to make it perfect and beautiful for me. Just whatever gets you going on the setup is great. Okay, so now I think I'm ready to start filling in the pieces. So I want this to end up being a function of x. X is the distance that Sue walks on the road. So that allows me to fill in this part right away. So I get a few things for free. The distance in the desert I'm going to have to work on still, but I do know the rate in the desert. The rate in the desert is 2 miles per hour. The distance on the road is x miles. That variable was defined for us. So I don't know exactly how far she walks, but I defined a variable specifically to represent that. So I'll use that variable. The rate on the road is 4 miles per hour. So we have all of the pieces without too much trouble, except for this distance in the desert part. So this is here where we get one final piece that we have to pull into this problem. If I want this distance right here, I'm just going to temporarily call it D. I need to get it in terms of x. So I did give it this temporary name D, but the truth is that my variable has to be x, and I can't put D in my final statement. So if it needs to show up in a step or two, fine, but when you're all done, there should be no D in your answer. In order to relate D back to x, I can see that of this 2 miles of distance total, I've used up x of them on the road, which means this part right here is a 2 minus x, running into my own writing. So if the entire length of this segment of road is 2 miles, and the right-hand segment of the road is x miles, then the left-hand segment is 2 minus x miles. The way I've drawn my picture, it almost looks like the two sides, the left and the right-hand side of the segments of the road could be equal, but you shouldn't be assuming that. Remember, x is a variable, so x could be a lot shorter than this or a lot longer than this. The only thing we know for sure is that these two lengths add up to 2 miles. So it turns out that if we want to get D, we have to use this triangle right here, and we'll need a Pythagorean theorem. So I have 1 squared plus a 2 minus x squared is equal to a D squared. So again, Pythagorean theorem says hypotenuse squared is equal to side length squared plus side length squared. And we're looking for d, not d squared, so we can just square root both sides. Algebra tells us that when we square root both sides, we should include a plus or minus, but we can make a judgment call here, so I'll write it for a second, but I'm going to make up my mind fairly quickly. This is supposed to be a distance. I am not going to look at negative distances, so I'll go ahead and choose the plus. I really don't care if you multiply out the 2 minus x times 2 minus x in the bottom. If you add the 1, it's really fine with me if you leave it like this. Not wrong to do that, but not required, so I'm just going to go ahead and leave it. Okay, so there is a complete setup. So again, quite a few pieces. We need the time as distance divided by rate piece. We need to recognize that because there are a couple of different distances and rates going on in this problem, we're going to have to split the time up into 2 different pieces. And we have to use that Pythagorean theorem in order to get one of our distances. I believe this one asks for a domain as well. It does. Okay, so reasonable domain. The smallest x value, we've actually already talked about the extremes. The extremes are cutting straight across to the parking lot and not walking on the road at all, versus cutting directly across to the road and spending as much of your walk as possible on the road. So cutting straight across to the parking lot would involve having an x value of 0. So I think that's our extreme again. And then if you cut straight across to the road and travel down the road for the entire 2 miles, that means x is 2. I see sometimes on this one that I get 3 as an upper cutoff for the domain, and I believe that where that's coming from is people looking at the total distance, 1 mile to get to the road and 2 miles down the road to get to the parking lot. But remember, x does not represent the total distance, it only represents the distance traveled on the road. So the biggest x can be in this problem, I would say, is 2. Again, you could argue with me if you want and say that really x could be bigger, we could shoot out this way and then come back to the parking lot. That's true, but I'm going to go far enough to say that that doesn't seem like a reasonable plan to me, and I'm going to cut it off at 2. All right, that's it for this one. Thank you for watching.